Great. Thank you for that wonderful introduction. So I thought what I would share with you today is my passion about mathematics and its connections both to technology and to scientific investigations. So I thought I would start off just kind of giving a broad list of some of the ways that you might not be aware mathematics is impacting your daily life. This ranges from things like internet services, when you do searches, streaming, things like Netflix or Amazon Prime, the use of your cell phone, not only in the design of the materials that go into your cell phone, the display technology, but also in important areas like data compression, which I'll tell you a little bit about in this talk. And there are other ways in which mathematics impacts your life, impacting the safety of the car that you probably drove yourself to work in, impacting things like the medicines that you use, given our increasingly sophisticated insights into things like cellular biology. So mathematics is really playing this role, often behind the scenes, and so I thought in this talk I would try to give mathematics a little more exposure and try to make some connections with these fields. So I thought I would start off by relating to a device that we all use on a daily basis, namely our cell phones, and in particular, looking at a common feature that we use, which is often snapping photos. None of that really would be possible without some pretty advanced mathematics that has occurred over the years. Let me just do a little quick back-of-the-envelope calculation for you. So suppose you have a camera like mine. If you look at the picture that you snapped, that's made of little tiny pixels. And if you do a little back-of-the-envelope calculation of the information content in those 16 million pixels, which is the typical resolution of these digital cameras we use, even if we represent each of those channels, the red, green, and blue, with just 8 bits, that's going to be over 48 megabytes of information, right? And so if you're like me and you kind of have a frugal data plan, let's say 1 gigabyte for the sake of the conversation today, that would only allow me to upload onto Facebook about 20 images, right? So clearly, we've got to do something, right, to overcome a barrier like that. And much of cell phone technology is like that, given the fact that when we make a cell call or we go on, our data plan when we're, not near, let's say, a wireless hub, there's a very limited electromagnetic spectrum that we're all sharing in order to transmit our information to that cell tower and ultimately to the cloud or to those internet services. Okay, so compression really is going to be key. So when you look at an image like that, right, you're not really seeing all 48 megabytes, right? What you're seeing is there's a beautiful church there, there's some lily pads, there's a fountain in the foreground. So really only a subset of the information content of that image is really perceptible to our eyes. And so what we really need is a good mathematical way to kind of sort out which part of the image we're paying attention to and which part of the image we really wouldn't notice if we threw it away. And so if we could come up with such an approach and let's say achieve a 10-to-1 compression ratio, that would allow my 1 gigabyte data plan to then upload 200 images, right? Clearly a huge improvement. Probably I don't have to think much about all those wonderful family photos that I share on Facebook or transmit to my friends on things like Snapchat. Okay, so image compression methods are really at the heart of this technology that we use on a daily basis. So I'm going to tell you about the JPEG standard, which is the typical way in which a natural image is stored and transmitted on the internet. So just to tell you a little bit about that information in the image that you can perceive, I need to say a little bit about our physiology and how we see images. So we have basically 2 types of photoreceptors in our eyes. We have the rods and we have the cones. And importantly, there are 3 different types of cones, and these cones are really the part that allows us to see color. The receptors that are sensitive to the short wavelengths of light, that's basically your sense of blue. You have this mid-range, which is basically your sense of green, and then you have this long-range photoreceptor to those wavelengths, which is basically your perception of red. So when you're seeing, you're not actually seeing color, you're seeing some combination of stimulation of those little photoreceptor, those cones in your eyes that are basically creating electrical signals that then through your optical nerve are processed in your visual cortex, and based on the weighting between those 3 different sensors, we perceive some type of color. I'll also mention that when we look at something like that image, we're not really seeing every single pixel, right? What we're seeing is sort of the broad strokes, the smooth variations in contrast. That's what lets us see that there's a church there or a fountain distinguished from the backdrop of that church. There's been a lot of work on trying to mathematically model our color perception, and I won't go too far in depth into that, but just mention that this research extends at least as far back to the 1920s when color print started to become quite widely used. And so there's something called the CIE standard observer, and there's basically a coordinate system which was designed to try to tease out the perceptually meaningful way the different aspects of how we see color. So here I'm just showing the CIE gamut. You'll notice there's a white spot in the middle, and roughly speaking, the angle is the hue. Is it red, orange, yellow, green, blue, purple? And then if you go from this white spot out to the edge, that's roughly telling you how saturated that color is. Is it purely red, or is it kind of a mixture with other colors? And there's 3 coordinates here, roughly corresponding to those 3 different types of photoreceptors. I'm just showing a cross-sectional plane. In a device such as the display that you're seeing on the screen right here, the trick isn't that there's a challenge that we can't generate just any arbitrary wavelength light very easily. So we play a little trick using this physiology. We have things like light-emitting diodes and color filters, which basically produce 3 colors, red, green, and blue, and then by cranking up or down the different knobs on those red, green, blue channels, we can achieve at least a subset of this color gamut, and that's given by that little triangle that I'm showing there. Okay, so this gives you some sense of how our eyes are perceiving things like color and texture in an image. So can we exploit that using mathematics in order to, again, throw away that sort of information that our eyes really are not going to notice so that we can achieve greater rates of data compression? I've told you about these red, green, blue channels that are often used in things like display technologies and representing our pixels and images. And so you can think of that as a point in 3-dimensional space where each coordinate is red, green, or blue. And now, in order to get things into a more perceptually meaningful representation, what you can do is a linear change of variable. And here what I'm going to do is do a change of variable where I look at the average intensity of a pixel. That's really this light and dark region, which your eye probably first notices. And then you kind of think about, is it more blue or is it more red? And so I'm going to have the average intensity y here, and then I'm going to have what's known as the blue chrominance or the red chrominance. And so this little change of coordinates, little linear change of coordinates, you can think of as like a little rotation of that 3-dimensional space, that little color cube that I've shown on the left. And I'm going to show you in a minute that this becomes really useful because I can then expend my limited budget of bits on the part that's more perceptually useful and spend a lot fewer bits on the part that my eyes don't really notice very well. This would be the red, green, blue channels broken down in this image if I do that little mathematical trick of changing the color space, fairly modest mathematics so far. Then I would have the intensity of the image represented, right? That's really in many ways the primary information contact. Many of us might be happy just to send that along. But then we can get color in there by having this blue chrominance channel and this red chrominance channel. And if you look, that in some sense contains a lot less information than the luminance. Luminance is really the dominant feature that you notice. So what you could do in theory, if you have this whole gradation of colors, is you can decide what budget of bits do you want to spend on it. And this is known as quantization. So if I say, all right, I just want to represent this whole spectrum with 3 bits, I have 8 possibilities. If I say 2 bits, okay, I have 4 possibilities. 1 bit, I got black or white, right? Okay, so this will come back later when I start talking about how I'm going to achieve compression. All right, now, what I mentioned a moment ago is you primarily notice smooth variations. So if I were to look at this image, I'll primarily notice that this is going light to dark. There's lots of little speckles in there, but you're not really noticing that. So I can do something called a discrete cosine transform, which I'm going to walk you through in a moment. Basically, the idea is I have this palette of patterns, and I can build up any of these textures that I see in an 8 block by combining together those fundamental little textures. Okay, so what is this discrete transform? So suppose I take just one little strip of this intensity. Let's just take the top row of this 8x8 block, so I can label them 0 to 7, and the pixel intensity as xn. And then what I could do is I can look at that as a function of the integers from 0 to 7. And just the height here is telling me how intense that is. And so you probably didn't notice this with your eye, but if you plot it, you actually find that it's got this overall shape and then these little wiggles superimposed on top. Okay, so how can I mathematically represent that in a way so I can kind of filter out the part which is perceptually meaningful and throw away those little wiggles which probably aren't going to affect the overall perception of that image? So what I can do is I can break this down just like I did here with my texture palette. I can do this in 1 dimension by writing this as basically a sum of a bunch of cosines that have different frequencies. And so by linearly weighting those together, I could reproduce this shape. So we can apply this transform from the pixel intensity data to weights on these fundamental modes by applying what's known as the discrete cosine transform. And what that does, if I were to plot now the weights that you have, you'll notice that this shape can be built up essentially of just the mode 0, mode 1, and then if I go way out here, mode 7 makes a little tiny contribution. And that's this kind of stuff that I want to throw away, the small contributions from the high frequency intensity variations. Suppose I now have my spectrum here and I decide to throw away that last value, just set it to 0. Then I can do an inverse discrete cosine transform. And so this is basically just taking these fundamental waves, building them up again using these weights to get some shape. And so if I do that through this inverse discrete cosine transform, I will get the pixel intensity that looks like this. Nearly indistinguishable, right, from the pixel intensity variation or texture that I showed you just a moment ago. Okay, so the similar thing has been done to get this two-dimensional palette, which is just taking the 8x8 blocks, these two-dimensional collections of pixel intensities, and I've just applied it now on each row, taken the result, and then done it on each column. And I can similarly filter then in frequency space and reconstruct my textures. Okay, so that's the basic idea for how to compress our image. The JPEG protocol is the following. We're going to take our RGB image data, we're going to transform it into this much more perceptually correspondent coordinate space, namely luminance, blue, and red chrominance, and then we're going to quantize. We're going to take our budget of bits and we're going to spend them in the way that's smart, mainly on luminance and a lot less on the chrominance channels. Then we're similarly going to do a discrete cosine transform on these little 8x8 blocks that I showed you a moment ago in frequency space, and then we're going to quantize. That is, we're going to take our budget of bits and we're going to spend most of them on the low frequency modes, and whatever's left over we'll spend on those high frequency modes if we have them available. And then any remaining data that we have, then we'll do some type of entropy encoding, something like Huffman coding. So what's the compression ratio that you've achieved through using this mathematical technique? There's some interesting aspects of the JPEG format that I don't have time to go into, but there's basically something called the quality. And you can control this. It's basically the budget of bits that I'm allowed to spend to represent my image. So let's suppose that I choose the quality factor to be 50%. Then I achieve a compression ratio of 6:1. So that's close to my goal of 10:1 that I mentioned in the beginning. I could take the quality factor a little bit more aggressively, down to 10%. In that case, I achieve an 18:1 compression ratio. And now notice some interesting things about the image. Basically, at the level of the overall picture, it really is not much change, right? It looks nearly identical to what I started with. If I zoom in now, just to kind of give a sense of how it affects different features at a, let's say, more refined level in the image, you can see I can still make out the people there. If I look at the person, though, he's a little more blurry, but that's still pretty good. You can make out that there's a person there. And no, he didn't go home and make a wardrobe change. He has a purple shirt on here, he has a blue shirt on there. That's a consequence of our quantization in those chrominance bits, basically throwing away information related to color, but still quite acceptable. Now, if I go really aggressive and I go down to a quality factor of 1%, then I gain really great compression, 51:1. But you see, I do pay a price for that. The overall image starts to look a little bit blocky, and you see the people descending the stairs aren't really very visible. You have green stairs, and this guy has totally been blobbed out into these smooth textures. So that gives you a sense of one area in which mathematics plays a very powerful role and works vigorously behind the scenes on our behalf in order to allow us to have such technologies as cell phones, where we're all sharing that very limited real estate, that electromagnetic spectrum transmitting back and forth to our cell phone towers. Okay, so in the second part of the talk, what I wanted to do is switch gears a little bit now that I've got you warmed up and talk about the role that mathematics plays in building new tools for scientific investigations and in improving things like the designs that we use in engineered devices and in personal products. So an area in which I work is stochastic modeling and scientific computation. So I thought I would give you a little bit of a sample of what stochastic modeling is all about. And so let's suppose we play a game. This is the probabilist favorite tool, this coin flip game. I flip the coin, and if it comes up heads, I win $1 from you, and if it comes up tails, I pay you $1. If we play that game, I think we all have very good intuition for what the outcome would be, right? You would either win $1 or lose $1 with 50-50 chance. There's some useful quantities that associate with this, namely the mean, that is the expected average value you'd get playing this game, which in this case would be 0, we break even. And the variance, the uncertainty in that outcome. I don't know if I'll actually win $1 or lose $1 in a given turn, and that's characterized by this variance, which is taking the deviations from the mean squared, weighted by the probability of those outcomes. Okay, so these quantities are really important, so I wanted you to get that in your mind as I go a little farther. So suppose I do 10 rounds of this game and we play. All right, what are the various outcomes? So I've plotted a little histogram of the outcomes here, and you can see that the probability that I lose all 10 times is pretty slim, and the probability that you win all 10 times is pretty slim as well. The most likely outcome starts to cluster around us breaking even, right? And if we play even more, it turns out that those extremes become even more rare, and you start to get more and more kind of the mean behavior arising. Although you do get this interesting characteristic shape for the distribution. Okay, so let's play a different game. Let's suppose you take a die and you roll it, and you have points from 1 to 6 based on the face values. I can again make one of these little histograms telling you the probabilities of the different outcomes. I can compute the mean and the variance. So on average, you'll get about 3.5. The variance is about 2.9. Now, what you can do is you could say, all right, well, suppose we play the game 10 times in a row. What do the outcomes look like? Surprisingly, the outcomes are starting to look qualitatively very similar to my coin toss game. In this case, the mean will be about 35, and then the variance will turn out to be about 29. And then I can do it 100 times, and you start to get even more similarity. In fact, this is pretty similar at this stage, to my eye at least. And so then you see that you get about 350 as your average score, and the overall variance goes like something like 290. Okay, so you see that you start to narrow around what that average value is. What's interesting is this characteristic bell curve is actually a very common feature when you look at random data. Basically, anything which is identically distributed, independent, and has a finite mean and variance will give you this so-called Gaussian distribution. So this is a very sort of deep result in mathematics, a consequence of a theorem you can actually prove, known as the central limit theorem. Basically says that if I rescale my samples like this, subtract off the mean, divide by the square root of the variance, and square root of n, that will always give me one of these standard canonical Gaussian distributions. That's really useful because it means that I don't have to worry about all these minute details of what went on in the random process. I just need to know some basic characteristics, namely its mean and its variance. Okay, so you can look at other phenomena, and so this has been done. People study things like, okay, what's the distribution of heights for ocean waves? Turns out to be a Gaussian distribution. You look at things like, well, many of you are in high school, you're about to take your SAT score exams. If you look at any given year at the scores, you roughly get, again, Gaussian distribution. And so it's all a consequence of that deep fact that if we take enough random events in aggregate, right, that the precise details don't matter of what the particular random phenomena is, provided it has a finite mean and variance. This goes back to this famous botanist, Robert Brown. He studied this flowering plant known as Clarkea puschella. He was very fortunate to live in London, and so he had many friends who could make really nice lenses, and so they made him this microscope, and he did something quite clever. He was trying to understand the process by which this plant would get fertilized, and so he was looking at the pollen granules. And so what he was able to do by changing the osmolarity of the water that this pollen granule was in, he was able to get it to burst and spill its contents. And so he started looking at the contents of that pollen granule, and this is roughly what he saw. So I've chosen this movie. It's not exactly what he saw. These are actually plastic beans. They're not pollen granules, since I thought it'd be clear. But he saw this spontaneously jostling of the little granules. And this was very mysterious to him. So at first he thought, okay, maybe this is just a manifestation of life. These things are swimming. It's part of the fertilization process. But he was a really good scientist, and so what he did is he took other inorganic compounds and he crushed them up and pulverized them also into little tiny granules, and he saw the same motion. And this was very intriguing to him, so much so that he published a pamphlet in 1828 describing his observations at length. If you notice, it has this title, On the Existence of Active Molecules. And so he was really begging for an explanation of this phenomenon that he felt was sort of generic to matter. Well, it's a very interesting and long story, but let me just tell you that within those observations, if you took that movie that I just showed you a moment ago, and you just looked at the y-coordinate over time, and you made a histogram of it, you would find that it would give us our favorite friend now, the Gaussian distribution. And in particular, the variance of that Gaussian distribution would grow proportional to time. And I've written it as 2D here just to have some notational consistency with theory in this area. Okay, so you get this Gaussian distribution which grows like 2dt over time. Well, it took about 80 years for this type of theory to be developed to explain Brownian motion. So one of the 1905 papers of Albert Einstein really was the first to come up with a satisfactory theory of Brownian motion, first of all, giving experimentalists a good handle on how they should be measuring Brownian motion. Don't look at things like particle velocities. Look at the mean squared displacement, like I showed you in that diagram. And then he furthermore made intricate arguments that was able to link the diffusion coefficient, that is how that variance grows over time, to the mechanics, namely the viscous drag of a particle through the fluid and the temperature of the system. And so this had all kinds of interesting downstream consequences, allowing for estimations of things like the mass of an atom, Avogadro's number, and so on. Then came along Paul Langevin and Marian Smolchowski, who then developed further theories, partly inspired by Einstein's work, in the language of classical mechanics, but now with randomized forces. And Wiener then came along and really put this on solid mathematical foundations by developing a measure theory on the space of continuous functions, basically a precise mathematical model for those little trajectories, and proved interesting theorems about Brownian motion, such as that it's non-differentiable in time, which leads to the requirements of a whole new calculus if you're going to deal with such randomized phenomena. Okay, so where does Brownian motion come from? So Brownian motion basically comes from this interesting process that there are more collisions sometimes on one side of a particle than another. And this all owes to the discrete nature of the water in which it's immersed. And so if you notice and you look closely at this movie, every now and then more particles will hit on one side, it takes a little bump. That process repeats, it takes another bump. And so Langevin's equation basically was to take Newton's famous, F equals ma, Newton's second law, and introduce into Newton's second law the appropriate forces, right? That's the way that you determine the trajectories of an object. And so there's our friend, right, a Gaussian. Because this process repeats in an uncorrelated manner over and over and over again, we should be able to aggregate them together and use a Gaussian distribution to model them. And that's exactly what Langevin did. And then here, this is just the viscous drag of the particle moving through the fluid. And here is any conservative force that acts on that particular system. OK, that's wonderful, and that works well for describing a small number of particles. But what if you want to describe particles which are subject to some type of hydrodynamic flow, or much more complicated situations where there are many, many, many of these particles, or the particles themselves have spatial extents, so they're going to undergo Brownian motion both at their center of mass and in their shape? Well, one idea is you could take, instead of modeling just the particle, you could think about how momentum is getting shifted around in that surrounding solvent fluid. And that's, in many ways, part of the research that's done in my group. And so what we could do is we could take that idea of a Gaussian random variable, but now make a spatially extended Gaussian random variable. And this is just showing, by solving fluctuating hydrodynamic equations, the momentum transfer that you get, which mimics the spontaneous transfer you had through those collisions from the solvent molecules. So this is going to be a very interesting mathematical way in which we can try to represent these collective interactions, or the Brownian motion of spatially extended objects. Let me just talk about how we can couple now the particle or the structure in back to the fluid that I've just shown you, that fluctuating fluid in particular. So if we go back to much of the technology that's been developed for macroscopic systems, we can get some good ideas about how to do that. One approach you might take is to have a separate model for, let's say, the elastic structure and the fluid. So the fluid flows over the structure, deforms it through traction stresses at the surface. The structure feeds back on the fluid through something like a kinematic condition, like a no-slip boundary condition. Well, that sounds like a great idea, and that works well if you're trying to optimize, let's say, airplane wing design for fuel efficiency, things of that nature. But if you're trying to study the kinds of problems that I just mentioned, that becomes really, really expensive. I'm just showing a finite element mesh here, because you'd have to refine all the way up to the level of the wing very precisely in order to get that traction stress correct. You could go to another extreme where you kind of throw the fluid away and you look at a particle subject to a force or a torque, and then you look at the flow that that induces by balancing the force of torque with the shear stresses in the fluid, and then look at the response, which would get you this hydrodynamic coupling tensor. That works well if you have spheres, but if you have any kind of polydispersity or structures that can deform, that becomes problematic. And so we've developed a overall framework for dealing with fluid structure interactions where we allow, again, for those two different descriptions of the microstructure and the fluid, and we have these abstract operators, lambda and gamma, which tells us how momentum is transported back and forth. So here's an example of one of the easier ones for me to explain within that framework. This is known as the stochastic immersed boundary method. So you can think of, just like our image that I showed you before, you could think of three-dimensional space divided up into these little tiny cubes. But now we have much more information in each cube, namely we have a velocity in each cube. And then what we can do is we can look at a way to mimic fluid mechanics, which is given by this differential equation here, in terms of rules for how momentum is exchanged between these little cubes. So this is the Navier-Stokes equations. And the Navier-Stokes equations has basically two important terms. The first one is this first term, which tells us how, if the fluid is flowing, how momentum is being transferred through the shear viscosity of the fluid. That's this term here. And the second term is telling us about the incompressibility of the fluid. So if I were to fill up a water balloon, with water, and I squeeze it, it will bulge to conserve its overall volume. And so this pressure serves to conserve volume. And that's this constraint here, the divergence of u being 0. OK, and then there is a third term, which is the overall particle force. And so any particles that are in the fluid, I will spread that as a force density locally around the particle. This provides a very efficient way, then, to couple fluids and structures. And so I can then have a kinematic equation for how the microstructure moves by simply averaging my local flow environment and then just moving at that averaged velocity. OK, so that works very well in practice. And so now what I can do is combine that with that idea I showed you before of this generalized, high-dimensional Gaussian random variable for how momentum is being transferred around through the molecular collisions into this model. And so what one has to do is come up with what that covariance structure is. And that can be done through a lot of sophisticated mathematical analysis, but ultimately is a consequence of the fluctuation dissipation principle. Okay, so it's our favorite friend, the Gaussian, which sits here. There are two parts to it. The first is this covariance, so it tells me basically how neighboring cubes here will randomly choose to handshake to give or take momentum from one another. And then if you do some very careful analysis, you find that in order to get consistency with statistical mechanics, you have to have this additional thermally induced drift, which is a consequence of the configurational momentum degrees of freedom not being conjugate in the Hamiltonian sense. Okay, so there's a lot of mathematics that goes into first just writing these equations down, and secondly, coming up with viable computational algorithms to simulate such a system like this. So I'll skip most of those details, and I will just tell you a little bit about how this relates to some of the products that you probably use on a daily basis. So, many of the shampoos, the hair gels that you put in your, hair in the morning, things like ketchup, there's all kinds of really subtle effects that occur at a molecular level that we'd really like to understand in detail and relate to those sort of macroscopic behaviors that we see. And so one of those, I'll just mention ketchup by way of example, is this xanthium gel, which is put in many, many different products. So the xanthium gum is put in there because it has this wonderful behavior of shear thinning. And so what you can do is put it in ketchup so that basically when I shake the ketchup or I bang on it, I know there's a big debate about which you should do, that will sort of loosen up the ketchup, that is, reduce its effective shear viscosity, and then it will flow, but then when it flows onto your French fries, it doesn't just stay all liquidy and everything, it thickens up again due to this xanthium gum that has that wonderful property. Okay, so relating what goes on at the microscopic scale to these sort of mechanics that we experience in everyday life is a really big and important challenge. And so this technique is one approach for getting some insights into those mechanisms. Okay, so what we've done is basically created a little computational rheometer. So a rheometer would be a device that you use to test the viscosity or the viscoelasticity of your particular gel or hair product. And you put it in there and you basically spin it at some constant, let's say, velocity, and you look at the feedback torque, and that tells you something about the stress given the particular stress rate that you were strain rate that you were deforming the material. Okay, so you can compute what the macroscopic stress is by taking a cut plane in this microscopic description. By looking at the forces that cross that cut plane, dividing by the area, that gives you an estimate of the macroscopic stress. Okay, so putting all those pieces together, we can get some insight into mechanisms by which you might achieve things like shear thinning. This is not exactly what happens in ketchup, but it's a similar type of a phenomenon. So if I take my little microstructures, in this case, they're little dumbbells that can't be stretched beyond some finite length, and you put them in a fluid and you shear, they'll tend to line up with the direction of shear. But because of that Brownian motion effect that I showed you, they'll tend to get kicked out of the shear plane, stretched, and relaxed. And this leads to a non-trivial shear viscosity. And so it's understanding the molecular level physics like that that's really important to somebody who wants to design a material or a product that has certain features. And so this is just showing how our methods could be used to compute something like the shear viscosity as a function of how quickly you've sheared. So if you don't shear very much, they're all jumbled around and you get a lot of lateral transport, therefore a lot of shear viscosity, right? Excess relative to the solvent fluid. If you shear very rapidly, they tend to align. There's not a lot of lateral transport of force, and you end up with a relatively low shear viscosity. So this is another one where I have a material which will exhibit thixotropy, and in particular, this material has the property that, very similar to the ketchup, that it's not until I really get things jostling that it starts to flow. I got to overcome some kind of yield stress in order to start the flow. And so what they have here are these little polymer filaments that are cross-linked, and these cross-links, as you see down here in red, if it's stretched too far, can break. Right? Okay, so let's see what happens if I then simulate this material. So if I simulate this material, it basically goes through 3 different phases. The first phase where the material starts to get ripped apart and those bonds break. The second stage where those polymers start to get stretched and then they relax to the shear plane. And in the third stage where there's an interplay between the shear stresses and the thermal fluctuations which drive them out of the shear plane, stretch and relax, stretch and relax. And so if you now plot that shear viscosity as I showed you before, you get something like this on the left. And so you can see that in the initial phase, I have a steep climb in the stress, and that is basically from stretching those bonds. That would be the yield stress. And then after I achieve that, then the material begins to kind of break apart and flow, and I end up with a shear stress that equilibrates to some equilibrium that depends on the temperature of the system. So I think I'll end on that node. And I hope I've given you some sampling of the important roles that mathematics plays not only in technologies you use on a daily basis, such as your cell phone, but also in developing new sophisticated computational tools that are affecting the kinds of products that we use on a daily basis. I thank you for all of your attention. This has been a lot of fun.